Hello once again, our most developed student. My name is Confident and welcome to the continuation of our topic, the waves, sound and light. And in this series of videos, I'm going to take you through all these topics that I'm showing you here. We have already looked at the transverse pulses. Now, we also looked at the transverse waves. So if you missed those videos, I'll encourage you to go back to the previous lessons. In this section, we are going to continue to look at the longitudinal waves, and then also it might be coupled with the sound waves. So let us dive straight into the lesson. This is already what has been covered under the transverse waves, the calculations. I did some previous question papers that you can expect, the type of questions that you can expect when you're dealing with transverse waves, as you can see. So all this has been covered in the previous videos. Now let's look at the longitudinal waves. Now when you talk about longitudinal waves, as you can see, it says here the second type of mechanical wave. So the first type was transverse wave, and then the second type of mechanical wave is a longitudinal wave. Now it also explains what a mechanical wave is. We are saying it disturbs the medium or the material, and the particles in the material move up and down in the transverse waves and to and fro in the longitudinal waves. Now that is what makes these mechanical waves. So the particles in the material, they move up and down. That's what we saw when we were dealing with transverse waves. So if you still remember, we were having a wave like this, and we are talking about to and fro, which is what we're going to discuss in the longitudinal waves. Now the most important thing is that, remember, energy, while the particles are oscillating to and fro, or they are moving up and down, what is just being transferred is that energy is transferred between the particles. Just remember that energy is being transferred between the particles. I'll just bring in at one time a video so that you can see what this means. It's better when you're demonstrating it. Now it says sketch a longitudinal wave. Now how do you come up with a simple sketch of a longitudinal wave? I'm just going to try to sketch something that will make sense to you and try to label it. So with a longitudinal wave, you have something like this. Then you have that. So you've got something like that. All right. Okay. Let me erase here. It was looking a bit. Then from here, I can take it. All right. Now, with this, so this is an example of a longitudinal wave, and if you are looking at it here, you can see that these points here, they are closer together. They've got 2 points, A, let's call it A and B. Now these points are closer together, so I put it in the center. Now these points that are closer together, they have a special name. The name of these points are called compressions. You see, because it's more like they are compressed. So these are called compressions, right? And then the points that are far apart, like for example at this point, I'm gonna make it longer, and that point I'll make it like the center. So these points that are far apart, they are called refractions or expansions. That's what you can use, expansion, they are further apart. Now this, let me call it C and D. Now with the compressions and refractions, now one thing you need to know about a longitudinal wave is that the particles are moving. This is the movement of particles to and fro. So remember that this is particle movement. All right, that's what makes it unique. They move to and fro. Don't forget that. And then, so the propagation of the wave, this is the direction of the wave. The wave is moving in this direction. So this is the direction of wave. In other words, the energy is moving in that direction. So what is unique now, you can see that the movement of the particle as well as the direction of the wave, they are parallel to each other. I'm going to bring that again as we look at the differences between the transverse and the longitudinal wave. But look at this distance here, if I can put this distance here, see that distance, that's which is from compression to compression, that's a wavelength. Or you can even use the distance here, C to D, from refraction to another refraction. That distance is called the what? It's called the wavelength. Just remember that. So whenever you are dealing with this kind of a wave, the distance AB, which is from compression, which is the center of the compression to the next center of the compression, is called a wavelength. Or from the center of a refraction to the next center of a refraction, what do you call that? You call it the wavelength. Now, if you are going to be looking in a way at an amplitude, the amplitude will be this particular distance. Let me use something, distance. From the center to the center, you will have here our amplitude. You see, that will become your amplitude. Center of the compression to the next center, the adjacent center, or the center that follows, which is the refraction. From the compression, you go to the refraction. So that becomes your amplitude. All right. So now this is in general what we can mean when we're talking about a longitudinal wave. So they might want you to sketch, but what is important when you're sketching, remember these things: the direction or the movement of first the movement of particles, or the direction of the movement of particles, or the direction of the motion of particles. You can even call this one direction of motion of particles. Okay, so they will want that, and then show the compressions, show the refractions, show the wavelength, as well as also show us the direction of the wave itself. Okay, so that is that part. So let's look at a few things here. It says in longitudinal waves, the particles what do? They oscillate. So to oscillate is it's a motion that is to and fro. If someone says you are oscillating, so this is the moment, the motion to and fro. So it's like back and forth kind of a thing. It's not the up and down motion, but it's the back and forth. The to and fro means oscillation. So the particles oscillate in directions parallel to the direction that the wave is traveling. That is very important, because that's what we show. We said the particles are moving. This is the movement of particles, which is horizontal, you see, and the direction of the wave, which is also horizontal. So you can say that there is parallel part. Now, I think automatically it brings back for me to remind you that this is not the case when you deal with the transverse waves. Transverse waves were at perpendicular to each other. So this was the particle direction, all right, and this was the wave direction. So remember that. So this was in perpendicular motion. So the particles were moving up and down while the waves was moving horizontally. So it was at 90 degrees perpendicular to each other, but these are parallel. Now compressions is the part of the wave where the particles are closer together. We saw that these were the compressions, A and B, as well as the refractions or expansions is the part of the wave where particles are further apart from each other. So remember, these are the refractions as we were mentioning, the C and the D. And then it says compressions are crests. See that now when you are trying to look at the similarity between transverse and the longitudinal wave. So if you come back to this diagram, they are telling you that this section of the wave compressions is like the crest. Remember, the crest is the highest position in a transverse wave. And now the refractions will correspond to the what? They will correspond to the troughs, which is the lowest point in a transverse wave. There it is. Compressions are crests and refractions troughs in the transverse wave. Now the wavelength is still similar, but it talks about compressions and refractions. What is the wavelength? In the transverse wave, we say it is the distance from crest to crest or trough to trough. But in the longitudinal, we're saying the distance between the center of one compression to the center of the next compression, or the center of one refraction to the center of another refraction. It is measured in meters. So here it is, if you look at A and B, A is the center of the compression, B is the center of the next compression. That distance is the wavelength. What about C and D here? If you look at C, my point C is the center of the refraction, and D is the center of the next refraction, and that distance is the wavelength. And then remember, in meters, rest or equilibrium position, this is the undisturbed wave. It is in the form, if I can say, the wave that is undisturbed. We are looking at a wave, for example, if I can sketch an undisturbed wave, this is a wave that is uniformly like that. There is no motion in that wave, it's just a uniform wave. That is a what? That is an undisturbed wave. The amplitude, which is the maximum disturbance of the particle from its rest or equilibrium position, that is distance from rest to crest or trough, remember, in transverse wave, and it is measured in meters. So here is the distance, remember, from rest of the wave, or we said from here it would be a what? It would be from a compression to a refraction, or from a rest to a refraction. That would be the amplitude in that part. And then frequency is the number of compressions that pass through a given point in 1 second. So these are the definitions that are important for you to know whenever you're dealing with the waves. And then we've got the period. It is the time taken for one full wavelength to pass a given point. Period is measured in second. The wave speed is the product of wavelength and frequency. So the wave speed, remember, V is f lambda. Very important. And it is measured in meters per second. Don't forget. Right. Now, the difference between a transverse wave and a longitudinal wave. This is also important for you to know. Now, first of all is the similarity. In the similarities, we did mention, let me take you back here to say what is similar between a transverse and a longitudinal wave. You need to know the similarities, and the similarities is here about being, number one, both of them are mechanical waves. That's what is similar. They are mechanical waves, number one. Number two, the particles of the material, they need a medium. You see, mechanical waves, they disturb the medium, so they both need a medium or material to move in. And we said there are three types of mediums: the gas, the liquid, and the solid. So they need these three types of medium, right? And then we are also saying in here, particles are not moving from one point to another, but they are oscillating up and down and to and fro. Only energy is the one that is transferred between the particles. So in longitudinal transverse waves, it's the energy that is being transferred between the particles, but the particles themselves, they are not moving, they're just oscillating to and fro and up and down. But now you will also look at differences here. The first difference, number one, that we did mention is that the particles in transverse waves, what are how the movement there? The movement are we can say are perpendicular to direction of wave. I know the English say is not good. So we're trying to say the movement of particles. So you can use it first to say movement. The movement of particles in transverse wave is perpendicular, not you can now say is perpendicular to the direction of wave. And in longitudinal waves, this is the thing now, longitudinal waves, how is the movement? That's where now they're trying to check if you are aware of the movement. The particles in longitudinal waves, particles oscillate or move in direction. That's where now they wanted to check parallel. See, that's the key part. You say perpendicular here we say parallel to the direction of the wave. So that's the main part. The particles in the transverse wave, they are moving perpendicular to the direction of the wave, but in what? In longitudinal waves, the particles oscillate in the direction that is parallel to the direction of the wave. That is the most important thing there that you can pick up. All right. And then you can also mention simple things that in transverse waves we talk of what? Crests and troughs. Okay. And then what about in longitudinal waves? We talk about what? We talk about compressions and what? And refractions. You see, those are the things that. And then simple one, though it's still fine, the movement in the transverse waves is up and down, while in longitudinal waves it's to and fro. You see, so this is the kind of movement, while the other one is this kind of movement. You see, so those are the things that you can bring in general, but the first one is important: the movement of particles perpendicular to the direction, parallel to the direction of the wave. All right, then with that it takes us to look at the sound waves. All right, now when you're going to look at the sound waves, I'm just going to introduce it, and then later we're going to cover in the next lesson where we'll look at the pitch, loudness and quality of the tone, as well as other parts. So we're saying sound waves. A sound wave is an example of a longitudinal wave. The sound waves are created by vibrations in the mediums in the direction of propagation, just like in what? In a longitudinal wave, the vibration causes a regular variation in pressure in the medium, thus causing compressions and refractions. Now, what are sound waves? Sound waves are said to be pressure waves. Sound waves travel well through air. Now, this is very important. They travel well through air, but better through a liquid and the best through a solid. Remember the three mediums. Now, it comes back to you remembering. Okay, I'll explain this in the next lesson. So it says, therefore, sound waves travel further and faster through a solid. This is because the more closely spaced the molecule of a medium, the faster the waves travel. The further apart the molecules, the slower the sound wave travel. In a vacuum, sound wave cannot travel because there is no medium or molecules for sound to travel. A sound wave is also a mechanical wave. So guys, because of time, I'm just going to end it up here. Join me in the next lesson, and in the next lesson, this is where we're going to begin. We're going to start with what? We're going to start with the sound wave here, and then take it further here, where we are going to look at the pitch, which is we're going to look at the pitch, and we're going to look at the loudness. All right, and then we'll continue to look in the same lesson at ultrasound, very important part of the lesson. So these are so much important for you to understand. And then later on, this is still a topic that is still open because we have not done electromagnetic radiation. So I'll encourage you, stay tuned to the next coming lessons, and you will be in a position to understand this topic. Thank you.